Scanner School, Session 2. What's the frequency, Kenneth?
Welcome to the Scanner School, a podcast dedicated to the scanner radio hobby. Class is about to begin. Here is your host, Phil Lichtenberger.
Welcome to our second session of Scanner School. I'm Phil Lichtenberger, W2LIE, and today we are talking about frequencies. Now, I just want to apologize in advance for the very dry subject matter here. Yes, this isn't the most exciting thing to talk about, and I hope you are able to understand that I want to teach you the fundamentals before we really start getting into the fun stuff. This is a very short episode, less than 15 minutes, and I promise you, the future episodes of Scanner School are a lot less dry. In our day-to-day lives, we deal with frequencies all day long. Lights, sounds, vibrations, our microwave ovens, the way we communicate, and of course, our radios. Our most familiar way that we use frequency is with our electrical systems, which is delivered commercially via AC power or alternating current. Inside the US, we have our power delivered at 60 Hertz, and in other countries, power is delivered at 50 Hertz. We'll talk more about Hertz later on. We all use a broadcast receiver or stereo at least a few times a week. The little numbers on the display, besides the time, will show you the exact frequency that the radio station is transmitting on where you are receiving them. So if you're listening to 102.3, for example, that is the frequency of the radio station. But what exactly is a frequency? The best way to define it is where everybody goes when they want to know a definition: Wikipedia. So Wikipedia defines frequency as the number of occurrences of a repeating event per unit of time. Okay, so what exactly does that mean? Let's think about it like this. Once a second, you take a sip of water. That frequency would be 1 time per second. If you were to carry this on for a full minute, you could say the frequency of you drinking is 60 times per minute. Right, so once per second, 60 seconds per minute is a frequency of 60 sips per minute. In radio frequencies, we talk about cycles per second. Well, we used to until we started using Hertz. A Hertz, abbreviated as a capital H and lowercase z, or Z for those of you outside the United States, is the unit of frequency in cycles per second. Now, Hertz is named after the German physicist Heinrich Hertz. Here is an easy way to remember this. Let's say instead of drinking a cold glass of water, you've poured yourself a boiling hot cup of coffee or tea. Maybe you prefer hot chocolate. I don't know, but whatever your choice of the morning beverage is, you make it so that is hot. Now I'm talking hot, hot. You take one sip of this drink and you burn your tongue. And let's just say you have no self-control and you take one sip of boiling beverage per second. That's a Hertz. One sip of the boiling water per second is 1 Hertz. 2 sips of boiling water in 1 second is 2 Hertz. 10 sips of boiling water in 1 second is 10 Hertz. So let's take a listen to an audible file so we can better understand Hertz. This chirp is set for 1 cycle per second, or 1 Hertz. Now this chirp is 2 cycles per second, or 2 Hertz. And this chirp is 5 cycles per second, or 5 Hertz. So as we increase the frequency, you'll notice that you are starting to hear the chirps more rapidly. So as you really start to increase it, you don't hear the individual chirps, you start hearing them more as tones. So we listen to 1 cycle per second, 2 cycles per second, and 5 cycles per second. Well, let's say 1 Hertz, 2 Hertz, 5 Hertz. Let's take a listen to 100 Hertz. Okay, and now here is 200 Hertz. And for those of you listening to this podcast on earbuds or headphones, we'll stop here at 200 hertz. I don't want to blow anybody's hearing. So in terms that we speak in radio, we talk about frequencies in kilohertz, or hertz of 10 to the power of 3. This is 1,000 hertz. In HF, or high frequency, and short wave, we normally see KHZ on our dials. 3,000 hertz would be 3 kilohertz. And we write this as 3, lowercase k, capital H, and lowercase z, or z. In VHF and UHF, we speak in megahertz, or capital M, capital H, lowercase z. Megahertz is hertz times 10 to the power of 6, or a million hertz. So 3 megahertz would be 3 million hertz. In the earlier example at the beginning of the podcast, we used a local FM radio station that your radio is tuned to in your car. And we said it was 102.3, which is in megahertz. If you were to look at this number in hertz, this would be 102,300,000 hertz. So another frequency you might be familiar with is in your Wi-Fi router. You'll see this as 2.4 gigahertz or 5.8 gigahertz. Gigahertz is hertz times 10 to the power of 9. Said another way, 2.4 gigahertz is 2,400,000,000 hertz. So something we will touch on later in a little bit more detail is wavelength. Talking about frequencies is a good start to that subject. Now, in order to understand more cycles per second, your wavelength has to shrink or compress, because you're adding more cycles into the same space or time. So think of a slinky or a coiled spring. As you stretch it out, all of the coils spread out. How many coils are in a given space? Well, not too many if you extend the slinky as far as you can. Now, compress that slinky and you'll see more coils in that same space. How easy is it to see through the slinky when it's fully compressed? How about when you pull it as far as it can go? See, as the frequency increases, your wavelength decreases. When your slinky is fully extended, that has a lower frequency and a longer wavelength. When you compress the slinky, you have a higher frequency and a shorter wavelength. So what else do you think decreases as your frequency increases? That's your antenna. Your antenna for 46 megahertz is pretty large compared to the antenna of your cell phone, which could be 700, 800, 900, 1900, 2300, or something else depending on where you live. Antennas are small enough where they can be engineered to be placed inside of your mobile device. No longer need that giant telescoping antenna like you did when you had the initial cordless phones when they first came out. Even your Wi-Fi antennas are being engineered to be placed inside of a computer, so you don't need to see them anymore. So what do you think more cycles per second would do to the distance a frequency could travel? Well, remember that slinky? Fully extended, it takes up a lot more space, but fully compressed is really not that long. In electronics, we like to use water as examples because we're all familiar with the way water tends to work or react to its environment. So say you throw a big rock into a puddle of water. You don't need much effort to create large ripples. If you drop a small rock into a puddle of water with the same force as a big rock, you'll notice a much smaller ripple or wake. It takes more energy or power to get a higher frequency to travel further. Without getting technical about wattage and power settings and all that, let's assume everything here is the same. Your Wi-Fi router seems to drop connection rather quickly the further you go from it. Sometimes you can't even cover a large house with a single Wi-Fi access point. But if you had a VHF radio in the same location pushing out the same power, in theory, it could go much further. And again, this is a subject we'll touch on in much greater detail in upcoming episodes of Scanner School. So let's go back quickly to wrap it up. If you take a sip of your boiling drink 1 time per second, that's going to hurt. 1 cycle per second is a hertz. If you're able to sip the boiling cup of coffee 1,000 times per second, on top of being incredibly stupid and painful, that's a kilohertz. And if you still have your tongue and your lips and you're able to sip that boiling cup of tea 1,000,000 times per second, that would be megaherting or megahertz. This session of Scanner School is sponsored by EastCoastPages.com. East Coast Pagers is a Unication, Apollo, and Swiss phone dealer serving the North American market. From one-way numeric and alphanumeric pagers to voice and P25 pagers, they have you and your department covered. Check out eastcoastpagers.com for Unication G1, G4, and G5 products and accessories. All Unication G1 pagers ordered from East Coast Pagers will ship with a spare set of batteries and a spare belt clip. East Coast Pagers will also ship your G4 and G5 pagers with spare belt clips. Complimentary programming of your department's dispatch and firegrounds are included. You can contact eastcoastpagers.com for a custom quote for your department. That's eastcoastpagers.com. I hope you have found this session and this podcast helpful. If you have any questions or feedback, please visit scannerschool.com/session2. From there, you'll be able to leave me a voice message with feedback, and I would love to answer your questions or use your feedback in future episodes. I use a service called SpeakPipe, and you can use your built-in microphone to leave voice feedback. Your messages can be left from your computer, your tablet, or your smartphone. In addition, on the post for this podcast on our website, you'll also find some bonus material that will go along with this podcast. Just fill out the form and I'll email you a PDF with some extra graphics and definitions that you can keep and refer back to later. Again, that link is scannerschool.com/session2. That's session with the number 2. Thanks again, and we'll talk next week about PL, DPL, and other methods of filtering out signals in your receiver. Until then, 73.
Thanks for listening to the Scanner School podcast. Be sure to visit www.scannerschool.com to access the show notes and bonus content.